Hi everyone. Today we're going to finish up chapter 17. And last time we talked about KSP, so the solubility product constant. And we said that molar solubility, or the amount of a compound that is soluble, is related to this KSP value. However, you cannot always compare solubilities of compounds by comparing their KSP values. So, in order to actually compare KSP values, the compounds must have the same dissociation stoichiometry. So, let's write out a little table here to just demonstrate what that means. So, let's say we have magnesium hydroxide. Oh, I put the parenthesis outside of the subscript. There we go. And let's say we're comparing that to iron to carbonate. And we'll write out their KSP values and then their molar solubility values. So magnesium hydroxide has a KSP value of 2.06 times 10 to the negative 13th. And its molar solubility is 3.72 times 10 to the negative 5th moles per liter. And then iron 2 carbonate, its KSP value is 3.07 times 10 to the negative 11th. And its molar solubility is 5.54 times 10 to the negative 6th moles per liter. Okay, so you'll notice that the KSP value for magnesium hydroxide is smaller than that of iron 2 carbonate. So I'll put a little symbol there showing that the KSP value for iron 2 carbonate is larger. But if we look at the molar solubility, magnesium hydroxide has the greater value. So we can't directly compare magnesium hydroxide and iron carbonate. And if we write out their dissociation, so in a different color here, I'll put the dissociation. So we would get magnesium and 2 hydroxides for magnesium hydroxide. And for iron 2 carbonate, we would end up with iron and carbonate. So we can see that the stoichiometry is different between magnesium hydroxide and iron 2 carbonate. So we can't directly compare these two. However, what if we add another compound to this table? Let's add calcium fluoride. Its KSP value is 1.46 times 10 to the negative 10th. And its molar solubility is 3.32 times 10 to the negative 4th moles per liter. Now, if we write out its dissociation, we have a calcium ion and 2 fluoride ions. So that means that we can directly compare magnesium hydroxide to calcium fluoride. And we can see that calcium fluoride's KSP value is greater than magnesium hydroxide's, and its molar solubility is greater than magnesium hydroxide's. So those two are directly comparable. So KSP is a little tricky that way. It's only really useful for comparing similar ionic compounds. Now, let's look at the effect of common ions on solubility. And this has to do with Le Chatelier's principle. So let's say down below we have calcium fluoride, and it's dissociating into calcium and fluoride ions. And if we add a soluble salt that contains one of the ions of the insoluble salt, that's going to decrease the solubility of the insoluble salt. So, for example, let's say that we also add sodium fluoride to this solution. So what we end up with are sodium ions and fluoride ions, but we already have fluoride ions floating around. So if we just kind of focus on what I boxed in here, because we're adding more product to solution, that's going to shift the equilibrium to the left. So again, this is Le Chatelier's principle. So if we're shifting this equation to the left, that means we're ending up with more calcium fluoride solid, and we're not allowing calcium fluoride to dissolve. So we're decreasing the solubility of calcium fluoride. And this is something that you can use in certain experiments. If you don't want calcium fluoride to dissolve, for example, you could just add more of a common ion. What about pH? How does that affect solubility? So down below we have magnesium hydroxide, and it's dissociating into magnesium ions and two hydroxide ions. Now, what if we increase the pH of this solution? So that means we're adding more hydroxide to solution. So if we're adding more hydroxide, we're adding more product. So that means equilibrium will shift to the left. So if we have a high pH, we're lowering the solubility of the hydroxide. Now, what if we add acid to this solution? So let's say we add some hydrogen ions. That means that we're going to see a reaction between hydroxide and hydrogen, which will produce H2O. And through that process, we're removing product from solution. So that's going to cause magnesium hydroxide to further dissociate, so we're shifting the reaction to the right. So if we lower the pH by adding acid, we're going to increase the solubility of the hydroxide. So this again has to do with Le Chatelier's principle. All right, now this is something we can use to our advantage. So for instance, let's say we have a pretty insoluble compound. Now again, even though we say that something is insoluble, it does dissociate to a very tiny extent. So it's not that it doesn't dissolve at all. It does dissolve to a very, very tiny extent. And let's say that we want to encourage that insoluble salt to keep dissociating. So we want to dissolve it completely. One way to do this is to add acid to the solution. Especially if you have an insoluble ionic compound that contains anions of weak acids. So one example is calcium carbonate. And this is something that's found in things like Tums, so it's kind of a chalky substance. And it can dissociate a little bit into calcium ions and carbonate ions. But if we want to encourage calcium carbonate to further dissolve, we need to add acid. So if we add acid, that's going to interact with this conjugate base, the carbonate ion, and it's going to remove carbonate from solution. And then we end up with bicarbonate and water. So this is super useful, for instance, in our stomachs. If you have an upset stomach because it's really acidic, if you take some Tums, which contains calcium carbonate, the carbonate ions will interact with acid and neutralize it. But additionally, by removing product from this equation, we're going to encourage calcium carbonate to continue to dissolve. All right, so a slightly different topic here is selective precipitation. So way back in Chem 161, we worked on a lab where we precipitated out different ions. So we mixed a few metal salt reagents with some anion test reagents. Some of them precipitated, some didn't. But in one part of that experiment, we had an unknown mixture of some unknown metal ion and silver. And we had to precipitate silver out of solution, but keep the other metal ion in solution. So that was the process of selective precipitation. We were selectively precipitating silver out of solution. So a solution containing several different cations can often be separated by addition of a reagent that will form an insoluble salt with one of the ions, but not the others. Now, a successful reagent can precipitate with more than one of the cations as long as their KSP values are significantly different. So we can use this in a process called qualitative analysis. And this is also called wet chemistry because you're using a lot of different solutions. So an analytical scheme that utilizes selective precipitation to identify the ions present is called qualitative analysis. So basically what we do here is if we have a sample that contains several ions, we're going to add several different precipitating agents in order to selectively remove certain ions. So we're going to remove them through precipitation. So here's a nice little diagram kind of showing what that means. So let's say we start with a mixture of different cations, and we'll label them A, B, and C. And A is represented by blue spheres, B is represented by black spheres, and C is represented by red spheres. And let's say we add our first precipitating agent, and it only reacts with cation A. So we're going to remove A through this process. Then all we have left are B and C, so we'll decant our liquid into a new test tube. And then we're going to add a second precipitating agent that only reacts with cation B. And then all that's left in the liquid is cation C, so we'll decant our liquid, and now we have just cation C left in solution. Oh, there's actually a typo up here. That should say C. So now maybe if you wanted to work with cation A, you could change the pH of the solution to extract out A. And then you could work with that cation on its own. And then you could do the same thing for B. Maybe once you've isolated your cation, you could redissolve it in a solution and work with that. So this is a pretty common form of chemistry. This method is a little outdated. There are some faster ways to do this now, but the same principles do apply. So this is a general qualitative analysis scheme. Basically, scientists were able to group different ions together, and if you follow this flow chart, you can kind of figure out which ions are removed during each precipitation event. And this can help you identify what's in an unknown solution of ions. So you'll notice that we have group 1, which contains insoluble chlorides. So silver chloride, mercury chloride, lead chloride. Group 2 has acid insoluble sulfides. So these are sulfides that are insoluble in acidic solution. So copper sulfide, lead sulfide, mercury sulfide, etc. Group 3 is made up of base insoluble sulfides and hydroxides. So these are compounds that are not soluble in basic solution. So aluminum hydroxide, iron hydroxide, and then we have some sulfides like iron sulfide, zinc sulfide, etc. And then in group 4, we have insoluble phosphates. So we've got calcium phosphate, barium phosphate, magnesium, ammonium phosphate, etc. And then group 5 contains our alkali metal ions that are always soluble no matter what. So these steps allow us to kind of separate and isolate these different groups. So the first step up above is to add 6 molar hydrochloric acid. And that's going to remove all of the insoluble chlorides. And then the next step is to add H2S and some more hydrochloric acid. So this creates an acidic environment, which means that any of our acid insoluble sulfides will precipitate out. And then from the remaining cations, we're going to add hydroxide next. And when we create that basic environment, this is going to encourage sulfides and hydroxides that are insoluble in basic solution to precipitate. And then finally, we add ammonium hydrogen phosphate and ammonia. And this is going to encourage insoluble phosphates to precipitate. And then finally, we'll just be left with our alkali metal ions. So let's go over some of those groups in more detail. So in group 1, again, we have silver, lead, and mercury. And if they're mixed with chloride, they can form insoluble compounds. So what we do is we add HCl, and then any of the silver ions that might be present in solution will react with chloride and produce silver chloride. And then it's the same with lead and mercury. So again, if you have a solution with a bunch of ions present and you're not sure what those ions are, you can always add HCl to remove silver, lead, or mercury that might be present. Then with the remaining solution, your next step would be to add H2S and hydrochloric acid. And that's going to promote the formation of insoluble sulfides. So for instance, maybe cadmium is present in your solution. Initially it's aqueous, and then it will react with any of the sulfur that's present from H2S and produce cadmium sulfide. So again, these sulfides are insoluble in acid. So that's why we also had HCl in solution. And then you can see some different sulfides here. So cadmium sulfide, it's kind of hard to see, but there is a little line there with a solid on the bottom. This is antimony sulfide and lead sulfide. So lead sulfide is not very pretty to look at. All right, so let's say we remove these sets of ions. So maybe we had cadmium present. Then whatever's left over, we're going to decant into a separate test tube. And next, we're going to try to precipitate out anything that is insoluble in a basic solution. So we're going to add more H2S, and we're also adding sodium hydroxide. Now, the reason that we're still adding H2S in this step is because some of the cations precipitate as sulfides, but some of the other cations in this group will precipitate as hydroxides. So for instance, iron 2+ will preferentially react with sulfur to form iron sulfide. And iron 3+ is going to preferentially react with hydroxide ions to produce iron 3 hydroxide. All right, so now once we remove any of those ions that might be present in solution, we'll decant whatever's left over. And then in group 4, we're going to try to precipitate out any insoluble phosphates. So that would be magnesium, calcium, and barium bonded to phosphates. So for instance, calcium will interact with phosphate to produce calcium phosphate. All right, and then in the last step, whatever's left over is something that is purely soluble or always soluble. And in order to identify which ion we have in this group, we could use a flame test. And flame tests will show different colors depending on which ion is present. So sodium, for instance, has a very orangey color to it when it's excited. And potassium has more of kind of a bluish purple color. So again, this is one way to try to determine what's present in a solution. There are other methods now that are quicker and faster, but again, it's always good to go back and review some of the old chemistry concepts. All right, so I think that's the end of our Chapter 17 discussion. There are a few more slides on complex ion formation. So if you are interested in these Lewis acids or transition metals, feel free to read the end of your Chapter 17 in the textbook. Otherwise, I think we will stop at this qualitative analysis, and you should have enough information to finish your homework as well, if you haven't already. So in the next video, we're actually going to jump backwards to chapter 14, and we're going to talk about rate constants. So I will see you in the next video.